hull of a boat to lower its center of gravity. By lowering the center of gravity, the boat becomes less prone to tipping or capsizing, making it safer and more seaworthy. The type and amount of ballast used depend on the specific design of the boat and its intended use. For sailboats, where the dynamics of wind and sail can be unpredictable, ballast is often vital for maintaining stability. Sailboats, in particular, face the unique challenge of wind-driven propulsion. The force of the wind in the sails can exert significant pressure, and without an effective counterbalance, a sailboat may tip or even capsize. To mitigate this risk, sailboats are equipped with a keel, which is a heavy fin or bulb-shaped structure located beneath the boat's hull. The keel's purpose is to act as a counterbalance to the force of the wind in the sails. By extending below the water's surface, the keel shifts the boat's center of gravity downwards and outwards, enhancing stability. The design of the keel is a sophisticated aspect of naval architecture, and it is tailored to the boat's specific purpose and the conditions it will encounter. For racing sailboats, keels may be designed to be more streamlined, while cruising sailboats often have heavier keels that provide greater stability but can reduce overall speed. The keel's effectiveness in counteracting the wind force in the sails ensures that the sailboat maintains its equilibrium, allowing for smooth and controlled navigation. Stability in boat design is a pivotal consideration in naval architecture. Whether for sailboats or other watercraft, achieving the right balance through weight distribution, ballast, and the design of counterbalancing structures like keels is essential for ensuring safety, comfort, and performance on the water. Boats designed with stability in mind are better equipped to handle the unpredictable forces of wind and water, providing both novice and experienced sailors with peace of mind as they venture into the world's waterways. Boats are equipped with rudders and other control mechanisms to change direction. The principles of fluid dynamics and hydrodynamics come into play here. The shape and position of the rudder determine how water flows around it, allowing the boat to turn. Boats are marvels of engineering that rely on a variety of mechanisms to navigate the water with precision and control. Among these mechanisms, rudders play a critical role in altering a boat's direction. The principles governing the operation of rudders are rooted in the intricate fields of fluid dynamics and hydrodynamics, which encompass the study of how fluids, like water, behave and interact with solid objects. The rudder is typically a flat, vertical surface mounted at the stern, back, of the boat. Its shape and positioning are carefully designed to facilitate steering. When the boat's operator or captain turns the steering wheel or tiller, it adjusts the rudder's angle in the water. This, in turn, influences how water flows around the rudder. The impact of these actions is what allows the boat to change its course. In essence, the rudder exerts control over the boat's heading by manipulating the flow of water. As water rushes past the rudder, it creates a pressure difference on either side of the rudder's surface. This pressure difference generates a force known as hydrodynamic lift, which then initiates a turning motion. The science behind this phenomenon is deeply rooted in Bernoulli's principle, which states that as the speed of a fluid, in this case, water, increases, its pressure decreases. When the boat's operator turns the rudder, it alters the water's flow pattern around the rudder, and, as a result, the pressure on one side becomes lower than on the other. This pressure differential pushes the stern of the boat in one direction, which, in turn, causes the boat to change its course. The effectiveness of the rudder's action depends on several factors, including its size, shape, and the boat's speed. Larger rudders and boats moving at slower speeds may require more effort to change direction. Additionally, the interaction between the rudder and other hydrodynamic elements of the boat, such as the keel, can also influence the boat's handling and turning capabilities. Understanding the principles of fluid dynamics and hydrodynamics as they pertain to rudders is essential for anyone involved in boating. From experienced sailors to naval engineers, it underscores the importance of rudder design and placement to optimize a boat's maneuverability and responsiveness to the helm.